In a few months, NASA will launch a $4 billion telescope toward a point in space 1 million miles from Earth. It will not orbit our planet. It will orbit an empty spot in the gravitational architecture of the inner solar system, swinging in slow halo loops around a place that, by all normal definitions, is nothing. From there, it will open a single infrared eye and begin an act of looking so patient, so vast, and so deep that the data it produces will still be yielding new discoveries a century from now. The astronomers who will make those discoveries have not yet been born. Some of them will use this telescope's observations to answer questions that, at this moment, we have not yet thought to ask. The telescope is called the Nancy Grace Roman Space Telescope, and it is, in some sense, a gift being sent forward in time, from us to a future we ourselves will never fully see. If you're new here, welcome. This is Cosmic Calm. Slow, carefully researched stories from across the universe, told at the edge of sleep. Let the words become distant. Let the images drift behind your closed eyes. There is nothing to remember, nothing to solve, just the long, quiet story of what humanity is quietly about to do next. Stay with me until the end. The universe is about to be seen for the first time as it truly is. Now, let us begin. Part 1. The Quiet Machine in the Clean Room. Somewhere in a sealed, white-walled room at NASA's Goddard Space Flight Center in Maryland, a machine is waiting. It is roughly 42 feet tall when fully extended, and it weighs about 8,000 kilograms. It has a single eye, a polished mirror 2.4 meters across, the same size, almost to the millimeter, as the mirror inside the Hubble Space Telescope that has been drifting above our planet for more than 3 decades. And yet, this machine is not Hubble. It is something else entirely. It is something that has never existed before in the history of human civilization. Its name is the Nancy Grace Roman Space Telescope. And in a few months, it will be lifted from this clean room, carried across the country to a launch pad in Florida, strapped to the top of a rocket, and sent 1.5 million kilometers from Earth, out past the Moon, out to a gravitationally balanced point in space called the second Lagrange point, where it will unfold, cool down, open its single infrared eye, and begin a survey of the universe so vast, so detailed and so strange that most of the people working on it quietly admit they do not yet know what it will find. They only know that everything we currently believe about the cosmos will either be confirmed, expanded, or quietly rearranged by what this one machine is about to see. And the strangest part is this: almost no one has heard of it. Part 2. A name carried forward. The telescope is named after a woman who changed the course of astronomy without ever leaving the ground. Nancy Grace Roman earned her doctorate in astronomy from the University of Chicago in 1949, at a time when women in the field were so rare she was once told, as a young student, that she should not pursue science at all. She ignored that. She joined NASA in 1959 as its first female executive and became its first chief of astronomy. And it was Nancy Grace Roman, more than any other single person, who convinced a skeptical agency and a skeptical Congress that the future of astronomy did not lie on mountaintops in Arizona or Chile or Hawaii, but in space itself, above the shimmering distortions of Earth's atmosphere, where a telescope could see the universe as it truly is. She is the reason the Hubble Space Telescope exists. She is the reason we have images of galaxies colliding 400 million light-years away. She is the reason a child born today can open a book and see, in color, the face of a dying star. She died in 2018, before the telescope that now bears her name was finished. But the people who built it say they think of her often. They say it is a strange thing to build an instrument named after someone who will never get to see what it sees. And yet, in another sense, she already did see it. She saw it long before the metal was cut, long before the mirror was polished, long before the first engineer was hired. She saw it in 1959 when she first stood in a NASA office and imagined that a human eye, lifted high enough, could see forever. Part 3. The question that will not let us sleep. To understand why this telescope was built, you must understand a question that has been haunting cosmologists for almost 30 years. In the late 1990s, two independent teams of astronomers, working separately and in competition, set out to measure how quickly the expansion of the universe was slowing down. Everyone assumed it was slowing. Gravity, after all, pulls things together. And the universe, we believed, had been expanding since the Big Bang, but more and more gently over time, like a ball thrown into the air that slows as it rises. The two teams measured the light of distant exploding stars, a specific kind called Type 1a supernovae, which act like cosmic mile markers because they all shine with nearly the same true brightness. By comparing how bright these stars looked to how bright they should look, you can calculate how far away they really are. And by checking how much their light has been stretched, you can calculate how much the universe has expanded while that light was traveling. What the two teams found, independently, in 1998, was something that made them stop and check their math for weeks. The universe was not slowing down, it was speeding up. Something, some unseen pressure, some property of space itself, was pushing the universe apart faster and faster. We gave it a name because we had to call it something. We called it dark energy. And almost 30 years later, we still do not know what it is. We only know that it accounts for roughly 68% of everything in the universe, and that it is growing stronger. That mystery, more than any other, is the reason the Nancy Grace Roman Space Telescope was built. Part 4. The Eye That Sees Wider. At first glance, Roman looks almost unremarkable. Its primary mirror is 2.4 meters across, the same as Hubble's, much smaller than the enormous gold hexagon mirror of the James Webb Space Telescope that currently hangs at the Lagrange point. If bigger mirrors gather more light, you might ask, then what is so special about this one? The answer lies not in what Roman sees, but in how much of it sees at once. Hubble's field of view is astonishingly narrow. When Hubble looks at the sky, it captures a patch roughly the size of a grain of rice held at arm's length. In that tiny patch, it can see galaxies 10 billion light-years away. But the sky is enormous. Hubble, in its 35 years of operation, has never come close to mapping even 1,000th of it. Roman's field of view, by contrast, is at least 100 times larger than Hubble's. Some of NASA's own briefings describe it as 200 times larger. In a single exposure, Roman will capture a patch of sky as wide as 50 full moons laid side by side. Its imaging sensor is 300 megapixels. Its raw data stream during flight will reach roughly 18 terabytes per day. The administrator of NASA, during a recent public unveiling, said something worth repeating slowly. He said, "Its surveying capabilities are over 1,000 times faster than Hubble." Let that phrase settle. 1,000 times faster. A survey that would take Hubble 10 centuries to complete will, on Roman, take about 1 year. Part 5. Horizon Moment Number 1. The scale you cannot feel. Here is what that actually means. Here is the thing you are holding in your mind right now that you may not yet have felt the weight of. Imagine every deep field image the Hubble Space Telescope has ever taken. Every spiral galaxy, every colliding cluster, every stretched and reddened smudge of light from the early universe. Every poster on every science teacher's wall, every iconic photograph that has shaped our cultural image of space for the last 3 decades. Now imagine all of that light, all of those galaxies, all of those discoveries, captured not over 35 years, but over 3 weeks. That is what Roman will do. Its first core survey alone, called the High Latitude Wide Area Survey, will cover more than 5,000 square degrees of sky, about 12% of the entire visible heavens, in just under a year and a half. In that time, it will photograph more than 1 billion galaxies, not observe, not detect. Photograph, in resolution as sharp as Hubble's, stretched across a sweep of sky so wide that there does not exist a computer screen in the world large enough to display a single one of its raw images at full size. This is the horizon moment. This is the first scale shift of this journey. When we speak about Roman, we are not speaking about a better camera. We are not speaking about an upgrade. We are speaking about an instrument that will, in its first few years of operation, gather more astronomical information than the entire previous history of astronomy combined. Every telescope ever built, every observatory on every mountain, every probe ever sent into the solar system, all of it, taken together, does not equal what Roman will produce in a single year. And it will do this silently, 1.5 million kilometers from Earth, orbiting a point in space where the gravity of our planet and the gravity of our star hold it perfectly still, its single infrared eye open to the dark, gathering the faint, patient light of worlds and structures and mysteries that have been waiting, some of them, for more than 13 billion years to finally be seen. And that is only the beginning of what it will do. When Roman finally begins its work, it will not look randomly at the sky. Its time is too precious, its instruments too precisely calibrated, its opportunities too finite for that. Instead, the mission is organized around 3 great surveys, each designed by more than 1,000 scientists from over 350 institutions across the world. These surveys have names that sound clinical, almost bureaucratic. The High Latitude Wide Area Survey, the High Latitude Time Domain Survey, the Galactic Bulge Time Domain Survey. But behind the clinical names lie 3 of the most ambitious observation programs ever conceived. The first will map more than 1 billion galaxies to chart the invisible scaffolding of dark matter and dark energy across the history of the universe. The second will stare at a single region of sky for years, watching for the faint flickers of exploding stars 13 billion years old. The third will gaze directly into the crowded, luminous heart of our own galaxy, cataloguing the births and deaths of stars and the hidden planets circling them. Together, these 3 surveys will consume roughly 75% of Roman's 5-year primary mission. The remaining 25% has been set aside for proposals from the wider astronomical community, discoveries that nobody has imagined yet, studies that will be dreamed up by scientists who are, at this moment, still in graduate school. That perhaps is the most quietly radical thing about Roman. It was built not only to answer the questions we have today, but to answer the questions we have not yet thought to ask. Part 7. The Deep Map of the Unseen. Begin with the first survey, the High Latitude Wide Area Survey. It will cover more than 5,000 square degrees of sky, about 12% of the entire heavens, in just under a year and a half. Roman will look far away from the dusty plain of our own Milky Way, looking up and out into the clear darkness beyond, where the light of distant galaxies reaches us undimmed by the stars of our own galactic neighborhood. In that sweep of sky, Roman will photograph hundreds of millions of galaxies in sharp infrared detail, and then it will do something deeper. It will measure how the shape of each galaxy has been distorted by the gravity of the invisible matter between us and them. Dark matter, the substance that holds galaxies together but has never been directly detected, warps space itself. Any light passing through a region rich in dark matter is bent slightly, the way light bends through a pane of warped glass. If you photograph enough galaxies and measure the distortion patterns carefully, you can work backwards and draw a map of the invisible material. Not a guess, not a statistical estimate, an actual three-dimensional map of where the dark matter is and where it was at every stage of cosmic history. No telescope in the history of astronomy has been capable of doing this on this scale. Hubble can measure dark matter in tiny patches, galaxy clusters, specific regions. Roman will measure it across 12% of the visible universe, reaching back in time more than 10 billion years. For the first time, we will be able to see the skeleton of the cosmos, and we will be able to watch it grow. Part 8. The Pulse of Exploding Stars. The second survey is different. Instead of a wide map, it is a deep stare. Roman will return again and again to the same patch of sky, totaling over 18 square degrees, a region roughly as large as 90 full moons laid side by side. For years, it will watch this patch, taking exposures repeatedly, cataloguing every flicker, every brightening, every fading light. The goal is to find exploding stars, specifically a particular kind of explosion called a Type 1a supernova. These are the rare detonations that occur when a white dwarf star, the smouldering ember left behind after a sun-like star dies, gathers too much matter from a companion and collapses in on itself. When it happens, the explosion is so uniform, so predictable in its brightness, that astronomers use these supernovae as standard candles, reference points to measure distances across the cosmos. In the 1990s, observations of about 50 of these supernovae led to the discovery of dark energy. 50. That is how many data points it took to overturn our understanding of the universe. Roman, in its time domain survey, is expected to find and study thousands of Type 1a supernovae, reaching much farther back in time than any previous survey has been able to. Astronomers estimate that Roman will observe these explosions at distances corresponding to the universe as it was 8 billion years ago, and some potentially even further. This will allow scientists to measure how dark energy has behaved across most of cosmic history, whether it has been constant or whether, as recent and deeply puzzling observations suggest, it has been changing over time. Part 9. The Heart of the Galaxy. The third survey turns its gaze inward, toward the center of our own Milky Way, toward the bulge, that thick, ancient, densely packed cluster of stars at the galactic core, a region crowded with more than 100 billion suns, many of them older than Earth by billions of years. Roman will stare at 6 carefully chosen fields in this region, each covering less than a third of a square degree. And every 12 minutes, it will take a new image of each one, not every hour, not every day. Every 12 minutes, for months at a time, across 6 different observing seasons spread across the 5-year primary mission. The reason for this relentless cadence is a phenomenon called microlensing. When a foreground star, moving through space in its own orbit around the galactic center, happens to pass in front of a much more distant background star, the gravity of the closer star acts like a natural magnifying glass. For a brief window, hours, days, sometimes weeks, the background star appears to brighten, then fade. And if the foreground star has a planet orbiting it, that planet leaves its own tiny, characteristic dip in the brightness curve. This is how Roman will find planets, not by seeing them directly, but by watching how they warp the light of stars behind them. Astronomers expect this single survey to discover more than 100,000 new exoplanets, including more than 1,000 that orbit far from their host stars. It will find rogue worlds drifting through interstellar space with no sun at all. It will find brown dwarfs, the failed stars that never quite ignited. And it will find something else, something we have only theorized about, never actually seen. Part 10, Horizon, Moment Number 2, The Invisible Graveyard. Here is what that something else is. Here is the scale shift you must feel next. Our galaxy, the Milky Way, is old, 13 billion years old roughly. In that time, hundreds of millions, perhaps billions of massive stars have lived, exhausted their fuel, and collapsed. When a star, many times the mass of our Sun, runs out of hydrogen and helium at its core, it does not fade gently. It collapses under its own weight, and in the final violent seconds, depending on its mass, it becomes either a neutron star, a core of matter so dense that a single teaspoon of it would weigh more than a mountain range on Earth, or a black hole, a singularity so gravitationally intense that not even light can escape its grip. Astronomers estimate that our galaxy contains roughly 100 million stellar mass black holes. 100 million. Drifting through the dark between the stars. We have only ever unambiguously confirmed the existence of a handful of them, and those we have seen only because they had visible companion stars nearby, whose behavior gave them away. The vast majority, the lonely ones, the ones drifting silently through interstellar space with no companion to betray their presence, have been completely invisible to us. This is the horizon moment. Until Roman, we have never had an instrument capable of seeing them, because microlensing does not care about light. It cares only about mass, and a black hole, even a lonely ancient black hole with no accretion disk and no companion star, still has mass, still warps space-time, still bends the light of any star that passes behind it, from our point of view. Roman is going to find them, not by the dozen, not by the hundred, by the hundreds, perhaps by the thousand, scattered across our galaxy like a hidden graveyard of collapsed suns that we never knew was there. For the first time in human history, we will begin to see the architecture of the dark, neutron stars with no companions, black holes drifting alone for billions of years, the silent remnants of massive stars that lived and died long before our own sun even formed. The galaxy we think we know is only the galaxy we can currently see, and what Roman will reveal quietly, patiently, 12 minutes at a time, is that beneath and behind that visible galaxy lies a second one, darker, older, heavier, and far more populated than anyone has ever seen. And this still is only the second chapter of what Roman will do. Part 11, The Second Eye. There is another instrument aboard the Roman Space Telescope, smaller than the Great Wide Field Instrument, mounted beside it like a second kind of vision. It is called the coronagraph instrument. It was designed and built at NASA's Jet Propulsion Laboratory in California. And while the Wide Field Instrument will do most of the scientific heavy lifting across the 5-year mission, the coronagraph will attempt something quietly more intimate. It will try to photograph other worlds, not indirectly, not by measuring a star's wobble or watching for the shadow of a planet passing in front of its sun, directly, as in a real image taken in visible light of a planet orbiting a distant star, with the planet actually appearing in the picture. This has almost never been done before. The few exoplanets we have ever directly imaged have been enormous, young, still glowing with the heat of their own formation, orbiting far from their host stars so as not to be drowned in starlight. Fewer than 100 have ever been seen directly across all of astronomy, and the reason is simple. Stars are so much brighter than the planets around them that trying to photograph a planet is, to borrow a phrase NASA itself uses, like trying to see a firefly next to a spotlight from miles away. or to describe an Earth-like planet around a Sun-like star, like trying to see a speck of bioluminescent algae next to a lighthouse from 3,000 miles away. The coronagraph instrument was built to make that impossible thing possible. Part 12. The machinery of light. Inside the coronagraph is a system of elegant, almost absurdly precise machinery. There are masks, small, precisely shaped obscurations that block the central glare of a star, the way you might hold your hand up to the sun to block it from your eyes. There are filters and prisms and detectors cooled to extreme temperatures to reduce their own electronic noise. And then there are the deformable mirrors. This is where the coronagraph becomes something that feels less like a camera and more like a living organ. These mirrors can flex actively in real time, adjusting their shape by amounts so small they are measured in fractions of a nanometer. Consider that. A nanometer is 1/billionth of a meter. The deformable mirrors inside the coronagraph can correct for imperfections smaller than the width of a strand of DNA. This allows the instrument to compensate for every tiny flaw in the telescope's optics, every faint distortion, every imperfection in the mirrors and lenses that would otherwise scatter starlight into the region where a planet might be hiding. The result of all this correction is something the engineers call digging the dark hole. When the coronagraph is working, the image around a distant star gradually darkens, almost as if you were slowly dimming a spotlight, revealing what was there all along, but drowned out by the glare. And in that darkness, a planet can appear. A single point of faint reflected light, billions of kilometers away, glowing gently in the stillness of another solar system. The coronagraph is rated to be roughly 100 to 1,000 times more sensitive than any coronagraph that has ever flown in space before. It is capable of detecting planets up to 100 million times fainter than their host stars. It is the most powerful starlight blocking instrument ever built, and it is a technology demonstration, meaning it is being sent not only to do science, but to prove that an even greater instrument can be built next. Part 13. The drifters. Step away from the telescope itself for a moment. Let us talk about what it will find. Among the most astonishing categories of discovery Roman is expected to produce are the rogue planets. The phrase itself sounds almost romantic, almost mythological. A rogue planet is a world without a star. A world that either formed alone in the darkness of interstellar space, condensing out of a cloud of gas and dust without ever being captured by a parent sun, or more commonly a world that was once part of a solar system, a normal planet, orbiting a normal star, and was then gravitationally ejected, perhaps by a close encounter with a larger planet, perhaps by the slow chaos of orbital resonances over millions of years, and flung out into the cold. These worlds drift now through the galaxy at tens of kilometers per second, with no sunrise, no sunset, no warmth from above. Their surfaces are locked in a darkness that has lasted in some cases for billions of years. We have only recently begun to realize how many of them there might be. Some estimates suggest that there could be more rogue planets in the Milky Way than there are stars, possibly trillions of them, drifting silently between the suns we can see. Roman will find them, by the thousands probably, because when a rogue planet, moving through interstellar space, happens to pass in front of a distant background star, the rogue planet's gravity briefly warps space itself, and the star appears to brighten for a few hours or a few days before fading back. No light is needed from the rogue planet. No signal, no heat, only mass, only the bend of space-time as it drifts through the dark. Roman's microlensing survey is expected to reveal these orphan worlds in numbers that will dwarf everything we have ever detected. Some of them likely will be the size of Earth. Part 14. The sensors. Consider what that means for our understanding of our own place in the universe. Before Roman, the overwhelming majority of known exoplanets have been found by one of two methods, either by the transit method, which watches for the tiny dip in brightness as a planet passes directly in front of its star from our point of view, or by the radial velocity method, which measures how a star wobbles slightly as a planet tugs on it gravitationally. Both methods are biased. They find large planets far more easily than small ones. They find close-in planets far more easily than distant ones. They find planets around bright, nearby stars far more easily than faint, distant ones. After more than 30 years of searching, we have confirmed the existence of roughly 6,000 exoplanets. Almost all of them are exotic by our own solar system standards, so-called hot Jupiters baking close to their suns, super-Earths larger than our own but smaller than Neptune, mini-Neptunes of a type that has no equivalent among the planets we grew up learning about. The planets like ours, rocky worlds, Earth mass, inhabitable zones, orbiting sun-like stars, we have barely begun to find. Roman is going to change this completely. Its galactic bulge time domain survey, combined with its other exoplanet finding methods, is expected to discover more than 100,000 new exoplanets. 100,000. And because microlensing is sensitive to a different range of planetary masses and orbital distances than the older methods, Roman will find for the first time the planets that have been missing from our census, the cold, far-orbiting worlds analogous to Jupiter, Saturn, Neptune, Uranus, and even the smaller ones. It will find analogues to almost every planet in our own solar system, except Mercury. For the first time, we will know whether systems like ours, a rocky inner solar system with cold gas giants in the outer reaches, are common or rare or almost non-existent. Part 15, Horizon Moment, number 3. The loneliness question. Here is what this means. Here is the third scale shift, and perhaps the quietest of them all. For as long as human beings have looked at the stars, we have asked one question, sometimes openly and sometimes in silence, sometimes in religious language and sometimes in scientific language, sometimes at the edge of childhood wonder and sometimes in the depths of adult solitude. The question is this: are we alone? Are there other Earths out there? Are there other worlds with oceans, with cloud weather, with seasons, with continents, with the slow architecture of life? Or is our little blue planet a miracle, a single improbable flicker in an otherwise lifeless cosmos? For all of human history, this has been a question of faith and speculation. And then, in the last 30 years, it has slowly been becoming a question of evidence. Kepler and TESS and the James Webb Space Telescope have given us thousands of data points, have shown us that planets are common, that Earth-sized planets exist, that some of them occupy zones where liquid water could theoretically exist on their surfaces. This is the horizon moment. Roman will take that growing body of evidence and turn it into a statistical map of our galaxy. When Roman completes its 5-year mission, we will, for the first time, have a demographic census of the planets in the Milky Way. We will know not just that they exist, but in what proportions. How many are like Jupiter? How many are like Saturn? How many are small, rocky, and Earth-sized? How many are in the habitable zones of their stars? How many drift alone with no sun at all? We will be able to calculate for the first time with real precision how many potentially habitable worlds exist within our galactic neighborhood. We do not know what that number will be. Estimates currently range from the hundreds of millions to the tens of billions. After Roman, we will know. Not with certainty about life, Roman cannot tell us that, but with certainty about place, about how many possible homes exist out there in the dark. And that, more than any other single thing Roman will do, changes the nature of the question itself. The question will no longer be, are there other worlds? The question will become, of the billions we now know exist, where should we look first? Part 16. The Mirror with Two Lives. There is something quietly extraordinary about the primary mirror at the heart of the Nancy Grace Roman Space Telescope. It is 2.4 meters across, polished to nanometer-level smoothness, lightweight, almost impossibly precise. And it was not built for astronomy. It was a gift. In 2012, the National Reconnaissance Office, the United States intelligence agency responsible for designing and operating the country's spy satellites, donated 2 unused 2.4-meter mirrors to NASA. These mirrors had been built for a classified satellite program that was either cancelled or restructured. The details have never been fully released. The mirrors were sitting in storage. They were the same size as the Hubble Space Telescope's primary mirror, but with a wider field of view and a shorter focal length, optimized for observing wide patches of Earth from orbit. It was a strange and unexpected inheritance. Imagine being given a mirror designed to look downward at our own planet, designed to peer into hidden places on the surface of Earth, and being told, "Here, take this, point it the other way, point it outward, and use it to look at the universe instead." That is almost literally what happened. NASA accepted the donation, evaluated the optics, and realized that the mirror's wide field of view was, by sheer coincidence, exactly what was needed for the kind of large-scale cosmological survey work that the astronomy community had been dreaming about for years. The mission concept that became Roman was, in a meaningful sense, made possible by a piece of hardware originally built to look in the opposite direction. There is a quiet poetry in this. A mirror designed for surveillance, designed to gather light from cities and roads and military installations on Earth, will instead gather the light of distant galaxies, the faint and ancient signals of stars that died billions of years before our own sun was formed. The same precision-polished surface, the same crystalline arrangement of atoms, the same engineering, turned away from us, turned outward, turned upward. A weapon's eye, repurposed into a telescope. A spy mirror given a second life as an instrument of pure curiosity. Some of the engineers who worked on the original program have said, off the record, that this is the better use, that this is what the mirror was always meant to see. Part 17. The Long Journey to Florida. In the summer of 2026, sometime during the warm Maryland months, the telescope will leave the clean room at Goddard Space Flight Center for the first time. It will be carefully wrapped in protective material, lifted onto a custom-built transport container and placed aboard a flatbed truck. Then, at a slow and deliberate pace, with police escorts and engineering teams in tow, it will travel south. The route is hundreds of miles long. The trip will take days. The truck will move slowly, gently, avoiding sudden braking, avoiding rough patches of road, traveling at night when traffic is light and the air is cool. Inside the container, the telescope will be sealed against contamination, cradled in shock-absorbing mounts, monitored constantly by sensors that track temperature, humidity, and any vibration that might disturb the precise alignment of its mirrors. Every bump in the road has been mapped. Every overpass has been measured. The telescope is, in a sense, like a sleeping animal, fragile, valuable beyond measure, and deeply trusting of the people who have built it. Its destination is the Kennedy Space Center in Florida, There, in the high bays of the launch processing facilities, the telescope will be unpacked, inspected, and prepared for its final encapsulation inside the payload fairing of a SpaceX Falcon Heavy rocket. The Falcon Heavy is one of the most powerful rockets currently in operation, a three-core configuration that, at full thrust, generates more than 5 million pounds of force at liftoff. It is overkill in some ways for a telescope that weighs only about 4.6 metric tons fully fueled. But the destination is far, and the precision required is enormous. The telescope must not simply reach orbit. It must travel 1 million miles. It must arrive at a precise location in the gravitational architecture of the inner solar system, slow itself with carefully calculated maneuvers, settle into a stable orbit around an invisible point in space, and then begin a multi-month commissioning period during which every system, every instrument, every cooling pump and reaction wheel and onboard computer is methodically tested and verified. Roman cannot afford to fail. It is the largest and most expensive astronomical mission since the James Webb Space Telescope, with a total program cost exceeding $4 billion. It is the highest priority mission identified by the entire United States astronomy community for an entire decade. There is no second copy. There is no replacement. There is only this one telescope, this one mirror, this one chance to send a single, irreplaceable instrument on a one-way journey into the dark. Part 18. The Place with No Up. The destination is called the second Lagrange point, often abbreviated as L2. To understand it, you must first understand something subtle about the gravity that holds the inner solar system together. The Sun pulls on Earth. Earth, in turn, has its own much smaller gravitational field. And in the geometry between them, in the specific places where the gravitational pull of the Sun and the gravitational pull of Earth combine in particular ways, there exist 5 mathematical points, the Lagrange points, where a small object can sit more or less stably without falling toward either body. The mathematician Joseph Louis Lagrange worked them out in 1772. He did the calculations by hand using only paper and ink, with no telescope, no spacecraft, no computer, more than 200 years before any human being would ever visit one of them. And yet, his solutions were perfect. The second Lagrange point, L2, lies on the line connecting the Sun and Earth, but on the far side of Earth from the Sun, about 1.5 million kilometers away. To put that in perspective, it is roughly 4 times the distance from Earth to the Moon. From L2, the Earth and the Sun are always behind a spacecraft, always in the same direction, allowing the spacecraft to cool itself easily by pointing its sun shield in one consistent direction and looking out into the dark in the other. L2 is, in a sense, a kind of permanent twilight. The James Webb Space Telescope sits there now. The European Space Agency's Gaia mission sits there. The Euclid Telescope sits there. And now Roman is going there too. It will not orbit Earth. It will orbit L2 itself, swinging in slow, looping arcs around an invisible gravitational point, carried gently by the combined pull of 2 bodies that, from where Roman sits, will both appear as small, bright objects close to one another in the sky. The orbit at L2 is technically called a halo orbit, because the spacecraft traces a wide, slow, halo-shaped loop around an empty point in space. It takes Roman about 6 months to complete one such loop. There is no surface beneath it, no atmosphere, no nearby bodies, just darkness, and the faint, distant warmth of the sun behind a thermal shield, and the slow pulling of two gravitational fields holding it in place. And from this position, this strange and lonely vantage point, Roman will look outward into the universe with no Earth in the way, no moon, no atmospheric haze, no satellite glint, no terrestrial light pollution of any kind. Just the cosmos, raw and unfiltered, opening before its single eye. Part 19. The River of Data. When Roman begins its work, the volume of information it produces will be staggering. The wide-field instrument generates raw images of 300 megapixels at a time. Across a 5-year primary mission, the telescope is expected to produce approximately 500 terabytes of data per year. To put that number into context, the Hubble Space Telescope, in its more than 35 years of operation, has produced a cumulative archive of roughly 400 terabytes. Roman will exceed Hubble's lifetime data output every single year. Each day, the telescope will downlink between 11 and 18 terabits of information through a global network of ground stations, facilities at White Sands in New Mexico, at the European Space Agency's New Norcia station in Western Australia, at the Japanese Space Agency's Great Antenna in Japan, and at the Deep Space Network sites scattered around the world. The data will arrive in vast streams, flow through processing pipelines designed by hundreds of scientists across multiple institutions, be calibrated, corrected, catalogued, indexed, and finally released to the global astronomical community. Roman will operate in significant part as an open data mission. Almost everything it sees will eventually be made available to anyone in the world with an internet connection and the desire to look. This is unusual. Most flagship telescopes have priority access periods, during which the scientists who proposed specific observations have exclusive use of the data for a year or more before it is released to the public. Roman, by design, has dramatically shortened these periods for most of its surveys. The reason is practical. The volume of data is too large for any single team to analyze. There will be more discoveries hiding in Roman's data than the entire professional astronomy community could possibly find on its own. So Roman will release its data widely, quickly, deliberately, allowing graduate students in Mumbai, amateur astronomers in São Paulo, retired engineers in Kyoto, and curious teenagers in small towns across every continent to download the same images that NASA's senior scientists are working with. Some of the most important discoveries from Roman in the years following its launch will likely come from people whose names are not yet known, from people who at this moment do not yet know that they will be the ones to find them. The data itself will be a kind of universal inheritance, distributed freely, an open invitation extended to the curious of every nation. Part 20. Horizon. Moment number 4. The telescope built for the telescope that comes next. Here is what most people do not realize about Roman. Here is the fourth scale shift, and perhaps the most quietly profound. Roman was not built to be the final word in space-based astronomy. It was built to be a stepping stone. NASA, the European Space Agency, and the international astronomy community have for years been designing what they call the Habitable Worlds Observatory, a future flagship space telescope, even larger than the James Webb Space Telescope, with a mirror potentially 6 meters across, designed for one specific and almost spiritual purpose: to find Earth-like planets orbiting Sun-like stars and to analyze their atmospheres for chemical signatures of life. Oxygen, methane, water vapor, possibly, if we are extraordinarily lucky, the spectroscopic fingerprints of biology itself. The Habitable Worlds Observatory is currently scheduled to launch sometime in the 2040s. It will be the most ambitious astronomical mission ever attempted, and it cannot be built without Roman first proving that the technology works. This is the horizon moment. The coronagraph instrument aboard Roman is not fundamentally a science instrument. It is a technology demonstration. Its job is not primarily to discover. Its job is to prove that a space-based coronagraph can suppress starlight by a factor of 100 million, to prove that deformable mirrors can correct optical flaws in real time in the hard vacuum and thermal extremes of L2, to prove that the algorithms work, that the calibration techniques work, that the integration of all these delicate systems can survive a rocket launch and the long cold journey out to the second Lagrange point. If Roman's coronagraph succeeds, and the dark hole tests on the ground have already exceeded expectations, performing better than anyone hoped, then the Habitable Worlds Observatory becomes possible. And if the Habitable Worlds Observatory becomes possible, then sometime in the 2040s, perhaps just within the lifetime of many of us listening tonight, a telescope will exist that is capable of pointing at a nearby sun-like star and producing, for the first time in human history, a single point of light that is unambiguously an Earth-like planet in another solar system. And then, with that single point of light in hand, we will be able to spread its faint photons through a spectrometer, separate them into a rainbow, and read in the wavelengths of light absorbed and emitted the chemistry of an alien atmosphere. We will be able to ask of that distant world the question we have been asking the universe since the beginning of recorded history: is anything alive there? And for the first time, the universe might actually answer. Roman is the first step on that road. Without Roman, there is no Habitable Worlds Observatory. Without the Habitable Worlds Observatory, there is no first image of another Earth. Roman is the telescope that was built to make the next telescope possible. It is the patient, foundational mission that will lay the groundwork for what may be, when it arrives, the single most important astronomical discovery of the 21st century. And it begins, this entire long road begins, with the launch of one observatory in September of 2026, lifted by a single rocket into a single careful trajectory, headed for a single point in space 1 million miles away. Part 21, The First Light. After the launch, after the long quiet coast through cislunar space, after the careful insertion into the halo orbit around L2, there will come a moment that the engineers and scientists involved in the mission have, in some cases, been waiting for their entire careers. It is called First Light. First Light is the moment when a new telescope, freshly arrived at its operating location, fully cooled, fully aligned, fully tested, opens its instrument for the first time and captures its first real image of the universe. For Hubble, first light came on May 20th, 1990, and the image was, at first, blurry, the famous spherical aberration of Hubble's mirror that would not be fully corrected until astronauts visited the telescope 3 years later and installed corrective optics by hand. For the James Webb Space Telescope, first light arrived on July 11th, 2022, with an image so deep and so detailed that scientists across the world spent weeks staring at it, finding new galaxies in every corner of the frame. For Roman, first light is anticipated to come sometime in 2027, perhaps 3 to 6 months after launch, depending on how smoothly the commissioning phase proceeds. The Roman project has already begun planning what those first images will show. The team is currently soliciting suggestions from the global astronomy community, asking for proposals for what they call first-look observations, a small set of carefully selected targets that will be photographed during the commissioning phase, intended both to test the telescope's full capabilities and to debut its powers to a public audience. Approximately 12 to 24 hours of commissioning time has been set aside for these first images. 3 to 5 programs will be selected. The targets have not yet been chosen, but the criteria are explicit. They must showcase what makes Roman unique. They must produce images that are scientifically valuable, but also visually arresting. They must, in some sense, be the kind of pictures that change what people imagine when they think of the universe. Imagine for a moment what those first images might show. A field of galaxies stretching to the edge of the visible universe, with the kind of clarity Hubble produced but spread across a swath of sky 100 times wider. A single image so dense with celestial detail that you could spend a lifetime exploring just one corner of it. Or perhaps the heart of the Andromeda Galaxy, our nearest large neighbor, photographed with Roman's wide field, every individual star resolvable, every dust lane visible, every cluster of newborn stars glowing in the infrared. Or perhaps a distant cluster of galaxies, with the gravitational distortions of dark matter visible as warped, stretched arcs of light from even more distant galaxies behind. Whatever the first images show, they will be unprecedented. They will be the first proof that all the years of work, all the billions of dollars, all the careful engineering and the patient testing have produced exactly the instrument that the astronomy community spent 15 years dreaming of. And from that moment on, Roman's real work will begin. Part 22. The Gold Standard of Open Science. There is something quietly radical about how Roman's data will be released to the world. NASA has made an explicit commitment that all of Roman's data will be publicly available with no exclusive use period. This represents a significant shift from how most large astronomy missions have historically operated. Traditionally, when a scientist proposes an observation with a major space telescope, that scientist receives priority access to the resulting data for a period of time, usually 6 to 12 months, before the data is released to the wider community. This priority period exists to reward the scientist for the effort of proposing the observation and to give them a chance to publish their findings before others can use the same data. It is, in a sense, the academic version of intellectual property protection. Roman has set this convention aside almost entirely. NASA has called it gold standard science. The reasoning is both philosophical and practical. Philosophically, it honors the legacy of Nancy Grace Roman herself, who spent her career advocating for the democratization of astronomical knowledge, for the idea that the universe belongs to everyone and that the tools we build to study it should serve the broadest possible community. Practically, the volume of data Roman will produce is simply too great for any single team to analyze. There will be more discoveries hidden in Roman's data than the entire global astronomy community can possibly extract on its own. By releasing the data immediately and openly, NASA is, in effect, inviting the whole world to participate. A graduate student in Lagos who notices an unusual pattern in a Roman image of a distant galaxy cluster might be the first person to identify a new class of cosmological object. A retired engineer in Helsinki, working through Roman data on a hobby project, might find the gravitational signature of a previously unknown black hole. an amateur astronomer in Buenos Aires, scanning Roman's microlensing data for unusual brightness curves, might detect the first definitive signal of a primordial black hole, a hypothetical type of object formed in the first moments after the Big Bang, never yet observed, but predicted by some theoretical models to be the missing constituent of dark matter itself. The data will be there for anyone who wants to look. The discoveries, in many cases, will not be made by the astronomers who designed the telescope. They will be made by the people who never had the chance to design any telescope at all, who simply downloaded the data and brought to it a different kind of curiosity, a different kind of patience, a different kind of eye. This is, perhaps, the truest legacy of Nancy Grace Roman herself. She would, one suspects, have wanted exactly this. Part 23. The Things We Cannot Predict. Julie McInerney, the senior project scientist for the Roman mission, said something during the unveiling press conference at Goddard Space Flight Center that is worth quoting carefully. She said, and I am paraphrasing only slightly to remove technical context, "I very much hope, and in fact expect, that the most exciting science from Roman is going to be the things that we didn't expect, that we couldn't predict, but that will set the new deep questions for future missions to address." This is, in some ways, the most important thing anyone has said about Roman, because the entire history of astronomy is, in significant part, a history of unexpected discoveries. When Galileo first turned a telescope toward Jupiter in 1610, he was not looking for moons. He was looking at a bright object in the night sky to test the resolving power of his new instrument. He found 4 moons. They changed the cosmos. When Edwin Hubble, working at the Mount Wilson Observatory in 1929, was carefully measuring the distances to nearby galaxies, he was not looking for proof that the universe was expanding. He was simply trying to map the local galactic neighborhood. He found that the galaxies were moving away from us, and that the farther away they were, the faster they were receding. This single observation gave us the entire framework of cosmological expansion, of the Big Bang, of the very idea that the universe has a history and an age. When the original Hubble Space Telescope was used in 1995 to photograph an apparently empty patch of sky for 10 days continuously, a controversial decision at the time since many astronomers felt the time was being wasted on darkness, it produced the Hubble Deep Field. The image revealed that the supposedly empty patch contained over 3,000 galaxies. The universe, we suddenly realized, was much fuller than anyone had imagined. None of these discoveries were what their telescopes were built to find. They were gifts. They were the universe rewarding the patient act of looking. Roman will look at more sky with more sensitivity across more wavelengths of infrared light than any previous wide-field survey telescope in history. The probability that Roman will find something nobody has predicted is, in the assessment of the scientists who built it, essentially 100%. We do not know what it will find. We cannot know. The only thing we can say with confidence is that whatever it finds will likely be more interesting, more strange, and more revealing of deep truths about the cosmos than the things we currently know to look for. Some of those discoveries will rewrite textbooks. Some will overturn theories that have stood for decades. Some perhaps will open entirely new fields of astronomy that do not yet have names. Part 24. The Long Inheritance. Consider for a moment the timescales at play. The Nancy Grace Roman Space Telescope is designed for a 5-year primary mission. After that, like most NASA flagship missions, it will likely operate for many additional years in extended mission status, depending on its instrument health and the value of the science it continues to produce. Hubble has now operated for 35 years. The James Webb Space Telescope, although younger, is widely expected to operate well into the 2030s and possibly beyond. Roman, similarly, may continue producing science long past its original 5-year window. But here is the deeper point. The data Roman gathers will outlive the telescope itself. Long after Roman has run out of the propellant it uses to maintain its orbit at L2, long after its instruments have degraded beyond the point of useful operation, long after the spacecraft has been decommissioned and gently nudged into a graveyard orbit drifting away from the Sun-Earth system. Long after all of that, the data archive will remain. It will sit on servers maintained by the Space Telescope Science Institute and by NASA's data centers. It will be accessible to anyone in the world, and astronomers, decades and even centuries from now, will still be using Roman's images and spectra to do science we cannot currently imagine. The same archive of Hubble data that was first generated in the 1990s is still producing major discoveries today, more than 30 years later. Researchers go back into the old files, apply new analysis techniques, ask new questions, and find things the original observers never noticed. Roman's data archive will be many times larger than Hubble's. It will be a permanent, freely accessible record of an unprecedented survey of the cosmos. It will be one of the great scientific inheritances of the 21st century, an inheritance left deliberately and democratically to every human being who ever wants to use it. And there is something quietly moving in the realization that the people who will get the most out of Roman's data have not yet been born. The astronomer in 2090 who finally cracks the puzzle of dark energy may do so by combining Roman observations from the late 2020s with new data from telescopes that do not yet exist. The biologist of 2150, searching for the chemical signatures of life in the atmospheres of exoplanets, may rely on Roman's catalogue of candidate worlds to know where to point the next great instrument. Roman is, in this sense, a gift we are sending forward in time. A gift to scientists who do not yet know they will receive it. A gift to a future that we ourselves will never fully see. Part 25. Horizon. Moment. Number 5. The largest question. Here is the final scale shift. The largest one. The one that, perhaps, this entire long voyage has been building toward. When you trace all the threads of what Roman will do, when you put together the dark energy measurements, the dark matter mapping, the rogue planet census, the supernova survey, the black hole inventory, the exoplanet catalogue, the deep galactic surveys, the coronagraph technology demonstration, and the open data archive that will outlive us all, you begin to see that Roman is not really a single mission with a single purpose. It is part of something much larger. Roman is part of a growing, multi-generational human project to answer the 3 deepest questions our species has ever asked. What is the universe made of? How did it become what it is? And are we alone in it? These 3 questions are, in some sense, the same question asked from 3 different angles. They are the questions that the first human beings sat around fires and asked of the sky. They are the questions that the great philosophers of antiquity wrestled with in their writings. They are the questions that drove the construction of every observatory, every telescope, every space mission ever built. And here now, at this moment in the early 21st century, we are quietly entering a phase of human history in which these questions are no longer purely matters of philosophy or speculation. They are becoming matters of measurement. They are becoming questions that can be answered with data. Roman will not answer them by itself. No single telescope can. But Roman will provide the most comprehensive set of measurements ever assembled to address them. And after Roman, the Habitable Worlds Observatory will continue the work. And after that, even more ambitious missions, instruments larger and more sensitive than anything yet conceived. And somewhere in that long chain of patient, deliberate human looking, somewhere out across the next century or 2, the answers will begin to crystallize. Maybe in our lifetimes, maybe in the lifetimes of our children, maybe further out than that. But they are coming. The universe, after 13.8 billion years of silent, indifferent existence, is finally beginning to be witnessed in the kind of detail that allows it to be understood. And we, this strange and curious species, perched on a small wet planet around an unremarkable yellow star in a quiet outer arm of an ordinary spiral galaxy, are the witnesses. We built the eyes, we polished the mirrors, we did the math, we launched the rockets, we unfurled the solar panels in the cold of L2 and pointed the cameras outward. And now we are about to see, truly see. For the first time in the history of our species, we are about to see what is actually out there. And whatever we find, whether the universe turns out to be teeming with life or stark and alone, whether dark energy is constant or changing, whether the cosmos is finite or infinite, whether our existence is rare or common, whatever Roman shows us, the act of finally being able to look will itself be one of the most significant moments in the human story. This is why Roman matters. This is why all of it matters. The mirror, the launch, the orbit, the data, the long, quiet years of patient observation. It is not about a single discovery. It is about the long and beautiful act of finally turning our eyes to the universe with instruments worthy of the task and asking it to tell us its story. Closing. We have traveled a long way together tonight. We began in a clean room in Maryland, watching engineers carefully integrate the final pieces of a $4 billion instrument named for a woman who once had to fight to be allowed into the field of astronomy. We followed the long history of the mirror itself, donated from a classified surveillance program and turned outward to look at galaxies. We watched the telescope travel south to Florida, lifted by a Falcon Heavy, carried out to the second Lagrange point, and unfolded into a position 1.5 million kilometers from Earth. We considered the three great surveys, the dark matter map of the cosmos, the supernova catalogue of the expanding universe, the relentless watch over the galactic core in search of exoplanets and black holes. We spoke of rogue planets drifting through interstellar space, of orphan worlds without suns, of the quiet inventory of 100 million stellar mass black holes that have always been there but have never been seen. We considered the coronagraph and the habitable worlds observatory that will follow, and the long road toward the first image of an Earth-like planet around a sun-like star. We held in our minds the staggering scale of Roman's data archive, an inheritance to be left to scientists not yet born. And we ended with the largest question, the one that Roman is part of answering, the one that may be the great question of our species. What is out there? And are we alone with it? And now, having traveled through these immense distances, you do not need to solve any of it. You can simply let the questions drift. There is no deadline tonight. There is no pressure to remember any specific fact. The telescope is real. It is being prepared. It will launch in the autumn. It will travel to its lonely orbit. It will open its eye and begin to see. And whether or not we are awake to witness any particular moment of that long unfolding, the universe itself does not require our witnessing. It is patient. It has been patient for 13 billion years. It can be patient for one more night. So let your thoughts soften. Let the images of telescopes and dark matter and quiet rogue worlds drift behind your closed eyes like distant stars seen from a darkened window. Let yourself be small and held and gently turn towards sleep. The universe is vast and you are a part of it. That is enough for tonight. If you enjoyed this slow voyage through the story of the Nancy Grace Roman Space Telescope, I hope you might consider subscribing to Cosmic Calm. New stories drift through here every week, bedtime documentaries from across the universe, told slowly, told carefully, told for those who, like you, find that the cosmos feels gentlest when approached at the edge of sleep. Leave a comment if you like, or share this with someone who might wander here too. Your presence here means more than I can say. For now, though, there is nowhere to go and nothing more to hold on to. The telescope will be there in the morning. The galaxies will still be turning. The questions will still be waiting, patient as starlight. Sleep well and good night.